Hi there, and welcome to Raelene Math. Let's talk about piecewise functions. Piecewise functions are functions that are defined on subdomains of the full domain of the function, and they're defined in pieces. We can have two or more pieces for it to be a piecewise function. Each piece or branch here is defined on a subset of the real line, the x-axis. So each of these vertical lines that I've drawn has an equation of x equal to a constant. We have x equals -3, x equal to 2, and we have x equal to 4 here. So we have region 1, region 2, region 3, and region 4. And each graph or each branch has been defined by a different function, and it's only valid for the x-coordinates that define that region. So region 1 is defined when x is less than -3, and we are not including that endpoint, so we don't include an equal to here. Region 2 includes the left endpoint, so we have -3 is less than or equal to all the way up to x is 2, but not including 2. So x is between these values, including -3, but not 2. Region 3 is a function which is linear, and neither the left endpoint or the right endpoint is included, and this is valid for x-coordinates that are between 2 and 4, but not including those endpoints. We also have a different piece of the function defined just at x equal to 4, which is just a single point, so that would take its own, I guess, line in the piecewise function definition. And then we have another branch over here in region 4, which is for x greater than 4. So these are the different subdomains that we would have. I said that we have 4 regions or branches, but we actually have this single point here which requires its own subset of the domain. So in theory, we have 5 different branches because this point at a single x-coordinate as opposed to an interval takes up a branch or a piece of its own. Okay, well here's the basic piecewise function. It's the absolute value of x. And the absolute value of stuff is defined to be negative times the stuff if the stuff is negative. Negative multiplied by something that is negative guarantees non-negative. The other option for removing the absolute value would be if the stuff is non-negative to begin with, meaning positive or 0, then we do absolutely nothing to the stuff to make that stuff non-negative. So what does that mean for the absolute value of x graph? Well, either, here we have stuff of x, we can either remove the absolute values by saying that the absolute value of x is identical to negative x or to positive x. We use the first definition if the stuff is negative, and the second definition if the stuff is non-negative, positive or 0. And so we can take a look at that graph. And in the graph of absolute value of x, we see this V shape, which is characteristic of the absolute value. What's really happening here is if we look at the graph of y equals x, we see that the y equals x graph has some y coordinates that lie below the x-axis, and therefore are negative, and some y values that are positive, which lie above the x-axis. The y-coordinates, or the heights in the graph that lie below, are the y-coordinates that change when we take the absolute value. And so it's like we reflected only the part of the red graph that lay below the x-axis to get the absolute value graph. In other words, we said that y is either equal to negative times x if x is less than 0, or y is equal to positive x. I'm just going to write x if x is greater than or equal to 0. And so if we turn off some of these other colors, including the blue one, we can see that the original blue graph we had is composed of a purple piece and a green piece. When we make a piecewise function, it's the same graph, so we want it all to be one blue function, one blue graph. Okay, so that's how we can take an absolute value and turn it into 2 pieces. Let's take a look at another example. In the next example, we have the absolute value of 3x plus 5, which I am going to call as a substitution name stuff. And so if we recall negative stuff if stuff is negative, or positive stuff if stuff is positive or equal to 0, we get this expression, and we have 2 linear functions defined on 2 different regions or subdomains. So if we look at those graphs, we can define them each individually. We can say y is equal to negative the stuff if the stuff is less than 0. Now in this program we can write it like this, and we can see at x equal to -5/3, that's where this graph is stopping its definition. But we can also solve this inequality for x and get that x is less than -5/3. Either way it works, the same thing. gives us the same thing. And we can come up with the second branch when x is greater than or equal to 5/3, and we say that removing the absolute value of stuff is equivalent to positive times stuff. Okay, and so we have our two branches, but they're the same graph, so we just use one color to represent the one graph. Now this vertical line of x equals negative 5/3 isn't part of the graph, it's just to show you where we defined on the left and on the right branches. We could also draw this graph as y equals the absolute value of 3x plus 5, and then the purple graph is the same as the blue one. If I turn off the blue, you'll see the purple underneath. Another way of thinking about this absolute value of 3x plus 5 graph is to think about the stuff inside, y equals 3x plus 5, and then do a partial vertical reflection at the x-coordinate that makes y 0. So anything of any part of the graph that lies below the x-axis flips up. And so if we do that, the partial vertical reflection will give us this blue graph, and we no longer have this purple part down below. Okay, let's take a look then at another example. In this, we'll go back to here. We have the y is equal to the absolute value of x squared minus 4. So if we consider what we just said, talking about the inner function first, we could draw this graph, which is going to be a parabola of x squared shifted down 4 spaces. And then we realize that the role of absolute value is to take any stuff that was negative and change its sign so that overall it's positive. So the stuff in here is the y-coordinate on the blue graph. And so the blue y-coordinates are sometimes positive, sometimes equal to 0, and sometimes the blue y-coordinates are negative. And actually I'm going to represent those negative blue y-coordinates by making them a slightly different color. I'll just write on top here. So all of these highlighted blue y-coordinates are negative ones. And so the role of the absolute value is to do nothing to the values that are not negative. So the absolute value will not change these y-coordinates, will not change that y-coordinate of 0, nor that one, and it won't change those y-coordinates which are positive. But all of these now bluey-yellow color y-coordinates are negative. For example, this y-coordinate is negative 4, and the absolute value of negative 4 is positive 4. So that y-coordinate will be reflected up to 4, and this point becomes 0, 4. So too will all the other points, and we'll get this red graph, which is a partial vertical reflection of the inside stuff, the x squared minus 4 graph. Let me just take a quick look at another function on the grapher to confirm. And we see that we get this graph, as opposed to the inner function. Let me draw this in red so it's the same colors that I had just been using. The inner function is just x squared minus 4, and if we turn off the red, we can see that we take the part that lies below the x-axis, where the y-coordinates are negative, and we reflect only that part vertically, and we get this red graph. Okay, so that's what happens when we have the absolute value in the function. This next example is a piecewise function as well because of the definition of the square root of x squared. If we're not careful, we'll think the square root and the squaring cancel, leaving us with x, but this is not true because the output of a square root function is non-negative. But x could be negative because x is variable, able to vary. And so we require the absolute value here to make this an identity for the square root of x squared. Let's just take a quick look at the square root of x squared to confirm. And the square root of x squared indeed is this modulus of x, or absolute value function. Okay, so now every time we see this square root of x squared, we can replace it with absolute value of x. And now we want to take a look at the rest of the graph, or equation, which says the absolute value of x divided by x. Well, if we recall our piecewise definition for absolute value of x, we had either negative x or positive x, depending on whether the inner stuff was positive or negative. And so now what we're going to do is divide by x. And so we are going to divide both pieces of the piecewise function by x. As soon as we introduce an x in the denominator, though, knowing that denominators cannot be 0, we get that x cannot be 0 in this example, and so we have to remove the definition of x equal to 0 from the domain. So we went from the blue graph, absolute x, having a domain of all reals, to this new function having a discontinuity or a domain restriction occurring at x contained in the reals except for 0. So we do always have to keep in mind what's happening to the domain with these piecewise functions. And we can simplify this. We see that negative x over x is going to be negative 1 as long as x is non-zero, and x over x is positive 1. So this function here is a piecewise function. We can break it apart as negative 1 whenever x is less than 0, or positive 1 whenever x is greater than 0. And from here, we can sketch this function over x. I'll turn this one off. And we see this piecewise function. If we trace along here, we see that when x is 0, y is not a number. And when x is 0, or approaches 0, we should say, really, from the right-hand side, y is not a number. Okay, so that gives us a new graph, and we do a lot of things in calculus with transformations of this graph. Here's an example of a transformation. It's not the most obvious transformation, so we'll have to do a little bit of factoring to see what's going on here. Inside the absolute value in the denominator, we can factor in x squared, and then we see a common factor of 2x minus 1. And so by applying the property of absolute values, we can take the denominator and separate it into absolute value of x squared times the absolute value of 2x minus 1. Now, thinking about the role of an absolute value and thinking about the graph of x squared, we know that x squared's graph has y-coordinates that are never negative. And so applying an absolute value to those y-coordinates does absolutely nothing. In other words, the square root of the absolute value of x squared and x squared are exactly the same. So I can remove these absolute values. So now my function simplifies a little bit to 2x minus 1. I still have the x squared in the denominator, just not in absolute value. And I'm going to write it a little bit differently actually. I'm going to write it as 1 over x squared multiplied by 2x minus 1 over absolute value of 2x minus 1. And so just as we had before, if we have the absolute value of stuff, we either get negative stuff or positive stuff, depending on whether stuff is negative or if stuff is greater than or equal to 0. Now if I put stuff in the numerator here, I've created a fraction where stuff is in the denominator, and so I still can't have stuff equal to 0. And then this first fraction simplifies to negative 1. The second fraction simplifies to positive 1 as long as stuff is not 0. What that means is that the stuff inside this bubble, which is like this stuff, is actually going to be positive or negative depending on what side of the root of 2x minus 1 we are. So the stuff I'm talking about over here is 2x minus 1. And so 2x minus 1 equal to 0 tells me that x equals 1/2. So my break is going to occur at x equal to 1/2. What I have then is that this is a piecewise function of either 1 over x times negative 1 or 1 over x squared times positive 1 for x less than 1/2 or for x greater than 1/2. And so when we draw this graph, we can draw it from the original function form, which doesn't require absolute value or piecewise notation with this curly bracket, or we can write it with the two pieces on the subdomains. So we'll define it the way it was given, y equals 2x minus 1 over the absolute value of 2x cubed minus x squared. And we can see that we get two different branches. And in these two different branches, it looks like we have a jump in height. Just going to change the range here a little bit so we can see the graph is going. I'll go from -4 to 4 along the y-axis. That doesn't make it much easier to see. I'll just go back to the original definition that we had. Okay, so we have our function like this and a bit of a jump happening. So I could also write the function in two pieces, either y equals -1 over x squared, and that 1 over x squared occurs when x is less than 1/2, or the second right piece or branch, y equals 1 over x squared, occurring when x is greater than 1/2. And so it's a bit difficult to see. I'll turn off the grid so we can at least see the graph matching. Come up with a slightly better range. Maybe we can go from -5 to 5. That helps us to see the graph a bit better. If I turn off the red, I'll have the purple on the left and the blue on the right, but remembering this is the same graph, so I want to use one color. So I could write the piecewise function defined by two pieces on two subdomains of the real line, or in this case I could have written it with only one function. And I get the same result either way. Incidentally, I see that as x approaches the vertical line of 1/2, I get two different heights, a height on the left of -4 and a height on the right of +4. And this is what we talk about in calculus as the one-sided limits, the left-hand height and the right-hand height. Whenever the left-hand height and the right-hand height are different and finite numbers, like we have here, going from a height of -4 on the left to a height of 4 on the right, we get what's called a jump discontinuity. Okay, let's take a look at another example. I want to point out the difference in using this bracket notation here. Here we have a bracket, and here we have a bracket. But there's two different meanings to the use of the brackets here. In the first case, we have an f of x function and a g of x function. This bracket in this example means and or intersecting, and so we have two graphs that are overlapping. Very often what we would do with a system of equations like this is look for intersection points. And so we would have a red graph, y equals x plus 1. We would have a blue graph, which is y equals x squared, and we would be looking to find out where the two graphs intersect. We would do this by eliminating one of the two variables. Now we have a red y and we have a blue y, so we could take the expression for one of them, substitute it into the other, and eliminate the y. So then we could solve for x from the single equation. And we would end up with two solutions which would represent the x-coordinates of the two intersection points. So I'm using two different colors for two different graphs. Meanwhile, over here, we only have one function, and that's, say, one green function, but it's defined on two different pieces. So we would take 1 over x and define that only when x is less than or equal to 1. Y equals 1 over x when x is less than or equal to 1. And we have a second piece of 2x squared minus 1 on the right-hand side of the vertical line of x equal to 1, so when x is greater than 1. I'm not going to use two different colors here because they're from the same one graph. And so when we see this, we get a graph looking like this. X equal to 1 is where we defined the two pieces. And at this point, the left-hand height approaches 1, and the right-hand height, or the height from the right, approaches 1. So those heights are the same. Furthermore, when x equals 1, we're using the first branch that was defined. So if I wanted to work out f of 1, I would use the definition corresponding to when x equals 1. So I would type in 1 here, or substitute it in, and I would get y is equal to 1. So I know that there's actually a full domain of all real numbers here. There's no x value that's excluded from the domain. And as a result, this graph is completely continuous at x equal to 1. There's a height when x equals 1, and then there's a height that y approaches on the left branch and the right branch. And all three of those values equal 1. It's the same single finite height of 1. Meanwhile, because of the 1 over x graph here, there's a discontinuity at x equal to 0, and there is a vertical asymptote when x is equal to 0. But that's not because of the piecewise function, it's just because of the rational function and its own domain restriction. All right, let's take a look at another example. We can have a piecewise function where the domain is almost entirely containing one function or one branch, and then we have a single element or a single piece on a second branch. Here we can take a look at the numerator function and simplify it a little bit. We can factor and get x minus 2 times x plus 1 all over x minus 2. So what we're really doing is saying that this function can be simplified to the reduced function of x plus 1 as long as x does not equal to 2. And that's an easy graph to sketch because it's a line. So we could sketch that graph. We're going to sketch it for all x coordinates, except when x is equal to 2. So I'm going to take x plus 1, which looks like this, and when x is equal to 2, I'm going to remove that point. And so I am introducing a hole in the graph. And so I'm saying when x is equal to 2, y doesn't equal to the height of the hole, of this point that we removed. It's going to be defined by the second piece, the second branch, which occurs only at a single x coordinate. Now, this should just be a y coordinate. It's a single number, but this function is making us work for it, and we have to define this first. And so we get sine of pi by 2, which is equal to, the sine of pi by 2 is 1. And instead of having a height of 3, we're getting the height to be at 1 instead. And so the graph looks like this. This filled in point is a single point on the graph, valid when x is equal to 2. Now, one of the things we might want to do is to redefine this function so that this graph is continuous. For this graph to be continuous, the height that y is and the height that y approaches need to be the same. Now, we can't change the height that y is approaching without bending both the left and the right-hand branches to infinitely many new heights. So instead, we redefine the height here, and we change it to the value to equal the limit value. So if we make the point 2, 3, we fill in the hole, and then the function is continuous. But then it wouldn't really make sense to use such a complicated expression to write this function, because this is a very simple function, just y equals x plus 1. In this last slide, I want to point out that the definition of the piecewise function is not only about what expression we choose to use for the left branch and the right branch, for example, but it also has to do with how we've assigned the x-coordinates on each subdomain. For example, if I wanted to work out f of 1 for the first function, I would take my x-coordinate of 1 and use the left branch piece, because that is the same branch that x is defined equal to 1. And so we say 3 times 1 plus 1 gives us 4. Meanwhile, for the g of x graph, when we want to substitute 1 into the function, x equal to 1 is not part of the domain at all, whereas it was part of the domain of the first function. In fact, the domain of f is all real values, but the domain of g is all real values except for 1. So always pay attention to the domain when we're trying to find functions, continuity, etc. So here we would have that the y value does not exist or is not defined to be any single finite y coordinate. And lastly, in the h of x graph, if we want to work out h of 1, we use the right-hand branch, because that's the part where the x is defined equal to 1, and we get negative 1 plus 2, which is equal to 1. And so we can see that these two function values, f of 1 and h of 1, are not the same because of how we've decided to substitute the x equal to 1, either into the 3x plus 1 or the negative x plus 2. If we take a look at this blue graph, the 3x plus 1, for example, we can see, and then the second one, negative x plus 2, we can see that we have a jump discontinuity. So it's possible that a piecewise function can be discontinuous, but we could also change this this vertical translation, if you will, and bring this right branch. I'm going to turn it red just so we can call it the red graph, or the red branch. We want to shift that up 3 spaces. So we could add 3 more to that and get the two graph heights on the left and the right to match. And then as long as when x is equal to 1, there's a solid filled in point there, this function would be continuous. So a piecewise function may be continuous, or it may be discontinuous, depending on how the functions and the subdomains are defined. So thanks for watching this video on piecewise functions. If you learned something, like the video, leave me a comment down below, and be sure to subscribe. Thanks for checking out Raelene Math.